Okay, so when we last left off, we were discussing nomenclature of aromatic compounds. So depending on what fundamental stem you choose for your ring, you can end up with a variety of different possible names. So for example, looking at the following compound, there are many possible names for this compound. I will generally prefer to choose phenol as my stem, just because we haven't yet covered nomenclature of alcohols, so it's best to include that in our stem. So for example, in this case, we have the stem of phenol, and now, of course, the group associated with our stem gets priority 1, numbering our remaining carbons. This is chapter 15 and page 8, right after where we left off in the notes. Perfect. So looking at our locant numbers, we now have the locant numbers for our other substituents. So we would name this as 3-bromo 2-methylphenol. Now, of course, there's an alternative name. If you choose to use toluene as your base, so if you use toluene as your stem aromatic ring, so you have this OH group is known as a hydroxyl group. This is known as a bromo substituent. So in terms of alphabetical order, if we had to pick numbering either clockwise or counterclockwise, which method is preferred? The method in red or blue? So if we have a tie and we have two substituents that can be assigned potentially the same locant number, what is our tiebreaker? What is our tiebreaker for this? Alphabetical order. So then, which numbering method is preferred? The numbering method in blue or red? Blue, yep. So we'd name this as 2-bromo 5 sorry about that, 5-hydroxyl toluene. We'll cover alcohol nomenclature later on. The key point that I just want to make is that you can write out a variety of possible names for the same aromatic ring following IUPAC rules. Does that idea make sense to everyone? Perfect. So let's keep going now, and let's try the following examples. Let's try to name the following compounds, and let's take about 3 to 4 minutes to work on these examples. And let's try to propose names for compounds A and B, following IUPAC rules. And don't be shy to share your proposed names for these two compounds in the chat, verbally or using the annotate tool. Does anyone have a proposed name that they'd like to share? Remember, the first order of business is to figure out an appropriate aromatic ring stem, an appropriate stem name, and then once you have assigned your locant numbers, you name each substituent and assign locant numbers to each substituent. So we have a proposal for this first, for A. So let's take a look. So A, the student chose the stem of phenol. Okay. The alcohol or hydroxyl group in phenol is priority 1. And we have 2 choices. So we have a methyl group, and this side chain is an isopropyl group. Okay. So in terms of priority, we have M versus P, okay? In terms of numbering, we have 2 possible options. So we can either number counterclockwise, or we can number clockwise. And my question to all of you is, which of these numbering methods gives you the smallest possible numbers? Red or black? What does the class think? Which of these numbering methods gives us the smallest possible numbers? In black, right? Because we have our first locant number as 2 rather than 3. Okay, so we have an isopropyl group. We have a methyl group at the 5 position. So alphabetically, the iso prefix isn't counted. So as a result, which of these substituents is first in our name? The methyl or isopropyl? Which one's first? The methyl, yep. So the methyl is first alphabetically because iso isn't counted in terms of alphabetical order. So this would be called 5-methyl 2-isopropyl phenol. Just remember that your stem, the substituent associated with the stem, gets the lowest locant number. Does this first example make sense? Everyone comfortable with this first example?
Yes.
I have a question. Can you please repeat the explanation why methyl is the first one again?
So in terms of prefixes, so like isopropyl, tert, butyl, the only prefixes that are counted alphabetically are sec and cyclo. These are the only 2 prefixes in IUPAC rules that are counted and considered for alphabetical order. So this isopropyl, the iso prefix, isn't considered when you think about alphabetical ordering of your substituents. And since methyl M is before P alphabetically, the methyl substituent goes first in the name.
That makes so much sense. Thank you.
Mm-hmm. I noticed there was another set of questions. The questions passed pretty quickly. We have some proposed responses for the second example, and we also have another alternative name. So we have 2. So in the one of the names that I see in the chat is 2-hydroxyl 3-isopropyl 6-methylphenol. The one piece of feedback I have is the name phenol already includes our alcohol. So you don't have to name the location of the substituent because it's already accounted for in the name. Another proposed name that I see is 3-hydroxyl. Let's see, 3-hydroxyl 4-isopropyl toluene. Okay, let me take a look and let's dissect that name. So for 3-hydroxyl 4-isopropyl toluene, if you chose to go through that naming convention and you chose toluene as your base, it would get priority 1 as your stem substituent. And you can either count clockwise or counterclockwise. The lowest numbers would be counting counterclockwise. So we have 3-hydroxy, 4-isopropyl, H before P. Yep. This name would be perfectly fine as well. Yep. Did that answer the question in the chat? So there are multiple possible names for these compounds. Does this first example make sense to everyone so far? Okay, let's look at this second example. Can we get some proposed responses and some proposed names for this second example? Although it has a lot of substituents, we can name it systematically via IUPAC rules. Does anyone have a proposed name for this compound? So we have a proposed name of 2,6-dibromo 4-chloro 3-ethyl 5-isopropyl phenol. And we see pretty consistent consensus between the responses. Let's talk about why that is. So we name phenol as our base. So this hydroxyl group gets priority 1. And we have 2 possible ways of counting. We can either count counterclockwise or we can count clockwise. And my question to all of you is, which of these counting methods is preferred and why? So we see a lot of students commenting that we have a little bit of variation. So would someone care to offer an explanation? So I see students saying the numbering method in red is preferred, the numbering method is in black is preferred. Why? What would someone care to provide a reason or an explanation? So we see someone commenting lower numbers are given to alphabetical order. So let's think about that for a moment. So this substituent is an ethyl group, yep, and this substituent is an isopropyl group. Now, both of these substituents can be assigned a priority number of 3. And my question to you is, which substituent is first alphabetically, ethyl or isopropyl? Ethyl, right? So now we're going to count counterclockwise, and that leads to the following name. So let's dissect that. So we have a bromine at the 2 position. We have an ethyl group at the 3 position. We have a chlorine at the 4 position. We have an isopropyl at the 5 position. And we have a bromine at the 6 position. Wait, so just to check the responses in the chat. So we agreed that ethyl is first alphabetically, right? So then the numbering method in black is preferred. Does that make sense to everyone? Because we assign a 3 locant number, the smallest locant number, to our ethyl group. So that gives us the following name that was provided in our student responses. So this looks perfectly reasonable to me. Does this second example make sense?
Could you also say orthobromo?
So ortho meta para is reserved for when you have exactly 2 substituents,
Oh, yeah.
or if you're describing the relationship between 2 substituents. For IUPAC, when you have multiple substituents, you have to resort to locant numbers.
Ah, yes. Thank you. Forgot about that.
No problem. Any other questions I can answer? Okay, so let's keep going now and let's talk a little bit about the structure of benzene and some properties of benzene. So for benzene, all of the carbon-carbon bonds are the same length, roughly 139 picometers, between that of a single and double bond. The electron density in all 6 carbon-carbon bonds is identical, and the structure is planar hexagonal. The carbon-carbon bond angles are 120 degrees, matching that of a sp2 hybridization. Each carbon atom is sp2 hybridized, and as a result, there's a p orbital perpendicular to the plane of our 6-membered ring. These p orbitals are conjugated, and our electron density is delocalized across all atoms in the ring. So when we think about 2 possible resonance structures, our resonance hybrid, which is the average of these 2 resonance structures, will have an average bond length, strength, and distribution of electron density of our 2 resonance structures. So looking at these 2 resonance structures, we notice that we have a bond order of 1 in our first resonance structure and a bond order of 2 in our second resonance structure. Averaging these together, we get a bond order on average of 1.5. So in our resonance hybrid, rather than having our carbon-carbon bonds be explicitly single or double bonds, this bond strength and length is closest to that of a 1.5 bond, in between that of a single and double bond. Does that idea make sense?
Can you please repeat that again?
So when you have multiple resonance structures and resonance contributors, you can estimate the average bond length, strength, and bond order by averaging and taking a weighted average of your resonance structures. So in this case, looking at our carbon-carbon bonds, we notice if we study a single carbon-carbon bond in detail, it has a bond order of 1 in one of our structures and a bond order of 2 in another structure. The actual structure that you see, which is your resonance hybrid, will be a weighted average of all of these resonance structures. And if we average out our bond order, we get an average bond order of around 1.5. So this bond, this carbon-carbon bond in benzene is closest to that of a 1.5 bond. Does that make sense?
Okay, yeah, it does. Thank you.
Perfect. So to help visualize the arrangement of orbitals in a benzene ring, so if we have an sp2 hybridized atom, perpendicular to the plane of our benzene ring will be a p orbital. Each of our carbon atoms, if it's sp2 hybridized, has a p orbital that can be utilized for bonding. And these adjacent p orbitals can overlap and engage in conjugation. And as a result, these conjugated p orbitals, we're able to delocalize our electron density across our ring and throughout our 6 carbon atoms in our benzene ring. So this double bond, or the double bonds that we observe in these structures, are not localized. Their electron density is delocalized across all atoms in our benzene ring. Does this idea of conjugation and delocalization look familiar?
Yeah.
Yes.
Perfect. So just a minor stylistic point, just one moment. The 2 benzene resonance forms can be represented by a single structure with a circle in the center to indicate that all of our carbon-carbon bonds have the same bond order and distribution of electron density. Though personally, when you're drawing mechanisms, it's often better to use these inaccurate but easier to handle localized structures just to make it easier to draw mechanisms. So like if you're drawing bromination of an aromatic ring, for example, it's easier to have a localized double bond that you can show explicitly the arrow pushing mechanism with. So when you're drawing mechanisms, it's often common to draw the localized structure with the double bonds explicitly noted, just so that way it's clear what bonds are being formed and broken in your reaction mechanism. Does that idea make sense? Okay, so let's keep going now. And let's talk a little bit about the stability of benzene. So first, we know benzene, despite the fact that it has alkenes, it has pi bonds, benzene will react slowly with bromine in the presence of a catalyst to yield bromobenzene, where bromine replaces a hydrogen. So rather than observing addition, instead, what we observe is substitution. Now, we'll talk a little bit about why we don't observe this addition product, but it stems in this idea that these conjugated pi bonds and these conjugated pi bonds arranged in a ring are especially stable. And throughout this lecture, we're going to try to understand the source of this stability and explain the reactivity and why aromatic compounds react in the ways that they do. So, the carbon-carbon double bonds in benzene are substantially less reactive compared to a typical carbon-carbon double bond. So for example, if you have hexene, for example, and you treat it with bromine, it will immediately and quite efficiently react to yield the substitution product. Oh, sorry. It'll yield the addition product. Sorry about that. One moment. Just to show the full mechanism, just as a refresher. And we end up with the dibrominated product. So your typical alkene prefers to engage in addition, while for aromatic systems, they prefer substitution. Does everyone see the stark difference in reactivity when we compare an aromatic system to a typical alkene? Okay, so let's keep going now. And let's look at heat of hydrogenation and how that serves as an indicator of stability. So the heat of hydrogenation measures the relative energy of carbon-carbon double bonds. Now, looking at the following example, if we subject each of these three reactants to reaction with hydrogen gas and exhaustive hydrogenation, all three of these reactants yield the same product, right? After exhaustive hydrogenation, each of these three reactants, we will end up generating cyclohexane. Does everyone see that? Now, we know that the enthalpy of a reaction is based on the enthalpy of formation of our reactants minus the enthalpy of formation of our products. And since we have the same product, formed in each case, the enthalpy associated with this hydrogenation reaction is proportional to the enthalpy of formation of our reactants and our reactant energy. So why does this matter? Why does this matter? Why does this matter? What have we figured out from this set of premises? Well, the products are identical, right? We're making the same product. So the difference in energy released during hydrogenation depends on the difference in energy between the reactant alkenes. The lower our reactant energy and the more stable the reactant alkenes, the lower the amount of energy released during hydrogenation. Okay, so we have a relationship between heat of hydrogenation and reactant energy. Now, if we look at the addition of hydrogen to a carbon-carbon double bond, it gives out about 118 kilojoules per mole, right? So if this process was strictly additive, then 3 double bonds would give 354 kilojoules per mole of energy released during hydrogenation, because 118 times 3 is 354 kilojoules. 3 double bonds. Okay. Let's look at some examples now, and let's see what happens when we start to look at conjugated systems. So cyclohexadiene, which contains 2 conjugated double bonds. When cyclohexadiene is subjected to hydrogenation, it gives off 230 kilojoules versus the expected amount of heat released of 236 kilojoules. So we have a difference of 6 kilojoules. Now, what is this difference telling us? Well, this tells us that cyclohexadiene is more stable than just a set of isolated alkenes. Conjugated systems are lower in energy. And we see that based on the lower than expected heat of hydrogenation. Does that idea make sense?
Can you say it again? Which one is more stable?
So cyclohexadiene is more stable than just an isolated set of alkenes because, as we can see, we'd expect if we hydrogenated and we subjected 2 isolated alkenes to hydrogenation, it would release around 236 kilojoules of energy. We observe only 230 kilojoules of energy released when we hydrogenate and when we react cyclohexadiene. As a result, we can conclude that because less energy was released during hydrogenation, cyclohexadiene is lower in energy than expected. And from that, we can conclude that conjugated alkenes are lower in energy and more stable than isolated alkenes. Does that idea look
Okay.
familiar?
Yeah.
Perfect.
Thank you.
Professor, one quick question.
Yes.
Can we
please go ahead.
say that the lower the energy, the more stable?
Yes. So
molecules?
the lower the heat of hydrogenation, the lower in energy your reactant, and generally the more stable the reactant would be.
Thank you.
Any other questions that I can address? Okay, so let's look now at an aromatic system. Well, benzene has 3 unsaturation sites. It has 3 carbon-carbon double bonds, but it only gives off 206 kilojoules per mole of energy. We expect if we hydrogenated 3 isolated alkenes, we would expect 356 kilojoules per mole of energy to be released. Thus, we can conclude, since less energy was released and substantially less energy was released, is benzene more or less stable than a typical isolated alkene? Are the alkenes, the carbon-carbon double bonds in benzene, more or less stable? Yep, as I see in the chat, they're substantially more stable. Benzene is substantially lower in energy than a set of 3 isolated alkenes. Further, we can estimate that benzene has about 150 kilojoules more quote unquote stability than an isolated set of 3 double bonds. This difference is pretty massive. And what we can conclude from this is that aromatic systems are unusually stable. And further, if we think about our difference here, if we think about the difference between a conjugated system and an aromatic system. So for cyclohexadiene, we got about 6 kilojoules of stabilization by having our double bonds conjugated. Now, if we added another conjugated double bond, we'd expect an increase of around 6 to 12 kilojoules, right, based on this trend. But instead, for benzene, having these 3 double bonds arranged, conjugated in a ring, gives us 150 kilojoules of stabilization. Can this 150 kilojoules be explained only due to conjugation? Are these two effects, are these two stabilizing effects the same order of magnitude? Just looking at the numbers.
Can you please repeat the question again?
So cyclohexadiene, it's stabilized by conjugation, and we get about 6 kilojoules per mole of stabilization. Benzene, with its 3 conjugated double bonds, gets 150 kilojoules per mole of stabilization. Are these two effects, are these stabilizing effects that we're observing, do these look like the same effect? Do these look like the same magnitude? Is the value for our stabilization the same or different?
The benzene is like way more in magnitude.
Yep, exactly. Benzene is way more stable. This stabilizing effect is way greater than that of simple conjugation. So aromatic systems are unusually stable, and aromatic systems are more stable than conjugated systems. So this effect is more than just conjugation. There's some other reason why aromatic systems are so stable. And what we're going to do now is we're going to dissect aromatic systems from the perspective of MO, or molecular orbital theory. Does this study of heat of hydrogenation, does this study, what we've gone over, make sense to everyone? Okay, so let's talk about pi systems and MO theories. So in molecular orbital theory, you generate molecular orbitals equal to the number of orbitals combined. So in this case, we're going to be studying and looking at ozone, as it has some pretty informative components. So ozone, so just reminding ourselves of the structure of ozone. Ozone has a Lewis structure that looks something like this. We can break down ozone and look at our conjugated pi system. And we have a pi bond and a p orbital that is conjugated to that pi bond. So in total, we've taken 3 p orbitals, and we're going to use those p orbitals, use those conjugated p orbitals to generate molecular orbitals. Now, in those p orbitals, we have 2 plus 2, 4 electrons. So we have 3 p orbitals and 4 electrons distributed throughout this conjugated pi system. Okay? So based on MO theory, if we take our 3 p orbitals, we will generate 3 molecular orbitals. Now, as a general rule, for each bonding molecular orbital that you generate, a corresponding antibonding molecular orbital is also generated. So in this case, we arrange our orbitals symmetrically about 0 energy. And in turn, we observe 3 unique types of orbitals with 3 different characteristic energies. So the first of which that I want us to look at is the bonding molecular orbital, shown here. So to help us understand what's going on with this bonding molecular orbital, let's recall and let's discuss what exactly is occurring with these p orbitals. So p orbitals are phased. So it would be proper to show one lobe of the p orbital shaded in. The phasing refers to positive and negative amplitude phasing. Just like if you think about it from the wave perspective, how a wave can have a positive or negative amplitude or phase. So based on the phasing of our p orbitals, they will overlap and interact in either constructive or destructive ways. Does this look familiar to everyone? Does this idea of orbital phasing and orbital overlap look familiar? Okay, so in the first case, when we have a bonding molecular orbital, we have effective overlap between orbitals and orbital lobes of the same phase. So we have overlap of regions with the same phase. We call this constructive interference. This is a stabilizing interaction. And when we have all of our orbital lobes of the same phase aligned and overlapped, we get a large stabilizing effect. So when regions of the same phase are overlapping, we generate what's known as a bonding molecular orbital. Bonding molecular orbitals are lower in energy because we are able to effectively distribute our electron density across multiple atoms, and we have a large number of bonding overlapping interactions. Does that make sense? Does everyone see how we have very good orbital overlap and we're sharing and distributing electron density across all of our atoms? Does that make sense to everyone? Okay, the next type of molecular orbital that you'll see is known as non-bonding. So non-bonding orbitals, in non-bonding orbitals, you will typically observe an isolated lone pair. So if we look at this central oxygen, you'll notice that it's not engaging in orbital overlap with any of our adjacent p orbitals. So it's neither bonding nor antibonding, and the electron density located on this central oxygen is instead held in a non-bonding orbital. It is not participating in bonding. Typically, when you fill the non-bonding molecular orbital in that structure, you will typically see an isolated lone pair. Does everyone see how the lone pair on this central oxygen is neither bonding nor antibonding? It's isolated. Okay. The other feature that I'd like to point out is when we have two regions of opposite phase, they will not overlap constructively. And so in turn, we end up with a node. So a node is formally defined. A node is formally defined as a region with 0 electron density. Now, why is this important? Well, the presence of a node indicates that we do not have, and by definition, we do not see a bonding interaction between our adjacent p orbitals. We have minimal bonding interactions. And so the more nodes we have, the less bonding interactions we have between our p orbitals, and in turn, the higher in energy this molecular orbital becomes. So in general, the more nodes that we have, the higher in energy our molecular orbital will be. So increasing nodes leads to increasing molecular orbital energy. The final type of orbital, a molecular orbital that we'll see are antibonding molecular orbitals. So what's the main feature of an antibonding molecular orbital? What do we notice? Do we see overlap between regions of the same phase, or do we see nodes present because we have multiple regions of opposite phase adjacent? So for our antibonding molecular orbital, we have multiple nodes. Yeah. And as a result, as we talked about earlier, because we have multiple nodes present, what can we say about the energy of this antibonding molecular orbital? Will it be high energy or low energy?
It'll be higher.
Yep, exactly. So now that we have our 3 molecular orbitals, you may not always see a non-bonding MO, but they are present. Now, once we have our molecular orbitals set up, we then populate it from the lowest to highest energy. So in this case, we fill our lowest energy bonding molecular orbital or orbitals first, then the non-bonding, and thankfully the antibonding molecular orbital is empty. Okay. So, key things to keep in mind: as you increase the number of nodes, orbital energy increases. So as you go up in orbital energy, you'll see more nodes present in your molecular orbital depiction. Does this discussion make sense to everyone? Does this look familiar from the previous organic course?
Did you say that as the number of nodes increase, then the amount of molecular energy also increases?
So as the amount of nodes increase, the molecular orbital energy increases. So these molecular orbitals are describing the distribution of electron density in our molecule and helping us describe molecular energy, but the energy of an individual molecular orbital doesn't match the overall molecular energy. Does that make sense? So the nodes are directly related to the energy for a given molecular orbital. And depending on which molecular orbitals contain electron density or do not contain electron density, these different molecular orbitals are utilized and can help describe reactivity patterns and help describe how different molecules will engage in chemical reactions. Does that make sense?
Yes, that makes sense.
Perfect. So let's look at benzene. So benzene is quite interesting because, as we know from the structure of benzene, we have a cyclic system with six carbons, and we have a total of 6 p orbitals. So we have 6 p orbitals, and in terms of the total number of pi electrons, we have 6 pi electrons. Now, if we take our 6 p orbitals found in benzene from each of our component carbon atoms, in turn, when combined, we will get 6 molecular orbitals. Now, from these 6 molecular orbitals, we will get 3 bonding molecular orbitals and 3 antibonding molecular orbitals. For those who are curious, how did we generate this arrangement of orbitals? There's a quick shortcut known as a Frost circle that we'll talk about in a moment. You draw your ring, and then you draw a circle around your ring. You split the ring down the middle, and then you draw a horizontal line at each point on the ring that touches the circle. So does everyone notice how from this Frost circle, we get 3 bonding MOs on the bottom and 3 anti-bonding MOs on the top? We'll see more examples of these Frost circles, but I just wanted to unpack how we got this exact arrangement of orbitals. Notice the bonding and anti-bonding molecular orbitals are arranged centered at 0 energy. So now that we have each of our bonding and anti-bonding MOs set up, we are going to fill our molecular orbitals from lowest to highest energy. We have filled these orbitals with our 6 electrons that we start out with, since we have 6 pi electrons. And as we notice, in benzene, we have 3 bonding orbitals filled with a total of 6 pi electrons, and our anti-bonding orbitals are empty. There's no electrons present in our anti-bonding orbitals. Now, why is this important? By occupying the bonding molecular orbitals, what do we notice about our electron energy? Are our electrons on average higher or lower in energy? Looking at this chart.
Lower.
Lower.
Yeah, lower.
Yep, exactly. So, in turn, by placing our electrons in these bonding molecular orbitals, our 6 pi electrons are in a lower energy state as they're more, and part of the reason for that is because these electrons are delocalized across a greater number of atoms in the ring. Now, there are a few terms that we need to know when we start to discuss these molecular orbital diagrams. The highest occupied molecular orbital, known as the HOMO orbital, is the highest energy orbital containing electrons. So as we notice in this case, the HOMO orbitals in this case are bonding molecular orbitals. The lowest unoccupied molecular orbital, or the LUMO, is the lowest energy orbital that does not contain electrons. And as we notice in this case, our LUMO is an anti-bonding orbital. So these 2 orbitals would be our LUMO orbitals. Now, we can conclude from this diagram, benzene is especially stable and considered an aromatic system since its HOMO orbitals are completely full and its bonding molecular orbitals are completely full. Does everyone see how in benzene, our bonding molecular orbitals are completely filled and we have not filled any of our anti-bonding orbitals? Does that make sense to everyone? Okay, so let's keep going now. And let's talk about aromaticity and the Huckel 4n+2 rule. So a ring system is considered aromatic if the compound contains a ring comprised of continuously overlapping p orbitals. So it must be planar and conjugated. So just to make sure everyone's on the same page, would a structure like this be viable when we talk about aromatic or non-aromatic systems? Would a structure like this satisfy the rule for aromaticity? Yes or no?
No.
No. The reason for that, it's not fully conjugated. Aromatic systems contain a ring comprised of continuously overlapping p orbitals. Second, a system is aromatic if it has 4n+2 electrons, where n is an integer whole number. So 2, 6, 10, or 14 are viable electron counts for an aromatic system. Aromatic systems are stable since their HOMO orbitals are completely full and their bonding MOs are completely full while the anti-bonding molecular orbitals are empty. We've seen this when we looked at benzene with its 6 pi electrons and 3 double bonds. Does this definition make sense to everyone? Does everyone see how 6 pi electrons corresponds to 4n+2? Because if n is equal to 1, we get 6 electrons. Does that make sense to everyone?
What does the n represent again for n plus 2?
N is just any integer whole number.
Oh, okay.
So
Thank you.
1, 2, 3, 4. And the 4n plus 2 describes a pattern of common electron counts that you see for aromatic systems. Does that make sense?
Yes, it does. Thank you.
Perfect. So let's talk about anti-aromatic and non-aromatic compounds now. A system is considered anti-aromatic if, first, the compound contains a ring of continuously overlapping p orbitals, and it contains 4n pi electrons. Now, we know that aromatic systems are stable since their HOMO orbitals are completely full and their bonding molecular orbitals are completely full, while their anti-bonding molecular orbitals are empty. When we start to look at planar cyclic molecules with 4n pi electrons, or anti-aromatic systems, these systems are much less stable than expected. We call this anti-aromatic. We see this in patterns of reactivity. These compounds will distort out of the plane and behave like ordinary alkenes. 4 and 8 electron compounds that are anti-aromatic actually don't exhibit a substantial amount of delocalization. Their double bonds will function very similar to an isolated alkene. So to show a few examples of this, cyclic conjugated systems with 4n pi electrons are considered anti-aromatic, and they react similar to isolated alkenes. For example, cyclobutadiene is so unstable that it will dimerize, and one of its alkenes will react very readily to generate this Diels-Alder adduct. If we actually look at cyclobutadiene in detail, it adopts a distorted geometry, almost a rectangular geometry, where we have different carbon-carbon bond lengths. So this carbon-carbon bond is very similar to a carbon-carbon single bond, while the double bond really is very close to that of a carbon-carbon double bond. This distorted structure tells us something really interesting. It implies that our pi electrons are more localized than we would expect. So for example, if we took our cyclobutadiene and we treated it with bromine, rather than engaging in substitution, it would likely engage in addition. So this double bond in an anti-aromatic system is very similar to an isolated alkene. Does this idea make sense to everyone? Okay, let's keep going now. So another example of an anti-aromatic system is cyclooctatetrine. Cyclooctatetrine, because it is anti-aromatic, rather than engaging in conjugation, it tries to minimize the amount of orbital conjugation by adopting a distorted non-planar geometry to minimize p orbital overlap. So cyclooctatetrine adopts almost a tub-like structure, and the reason for that is it makes it much more difficult for the entire set of p orbitals in the ring to engage in effective conjugation. So cyclooctatetrine adopts this distorted geometry to minimize orbital overlap and thus minimize some of this destabilizing anti-aromatic effects. So the alkenes in cyclooctatetrine are unstable and they'll react similar to an isolated alkene. So you can brominate, you can dihydroxylate, you can engage the alkenes and cyclooctatetrine in addition reactions. So the alkenes and cyclooctatetrine are very similar to isolated double bonds. Now, it's important to note that if we look at heats of hydrogenation, we actually see that the heat of hydrogenation for cyclooctatetrine is actually greater than the heat of hydrogenation for 4 alkenes, right? If we take 97 times 4, that gives us 388 kilojoules. So we'd expect 388 kilojoules of heat to be released, assuming these alkenes were behaving just as simple isolated alkenes. In reality, we see 410 kilojoules per mole of heat released. And this tells us that anti-aromatic systems are less stable and higher in energy than aromatic and simple conjugated systems. So it's not just that anti-aromatic systems are not stable, they are actively unstable and destabilized. Does that idea make sense? Okay. Let's keep going now. So when we think about anti-aromatic systems from the perspective of MO theory, a central premise is this idea that anti-aromatic systems are unstable since their HOMO orbitals are half full. We call this an open shell system. Further, anti-aromatic systems place their highest energy electrons into non-bonding molecular orbitals or anti-bonding molecular orbitals. Now, if we look at, for example, cyclooctatetrine, in this case, we're looking at cyclobutadiene. As you notice, we have 4 pi electrons, so 4n, n equals 1, 4 electrons. So this is an anti-aromatic system. We have a total of 4 p orbitals to work with. And we're going to take those p orbitals and use those p orbitals to generate molecular orbitals. Okay, applying our Frost circle once again, we generate 1, 2, 3, 4 molecular orbitals. So we have 1 antibonding, 1 bonding, and then 2 non-bonding molecular orbitals. Now, from our molecular orbital diagram, we then take our 4 pi electrons and we fill our molecular orbitals from lowest to highest energy. Okay, so with that established, as we notice, when we fill these orbitals from lowest to highest energy with our 4 pi electrons, we notice first and foremost that our highest occupied molecular orbital is half filled. That's a destabilizing interaction. Further, what orbitals are we filling up here? What type of orbitals are we filling? What do we call these orbitals? So the orbitals right at 0 energy, what do we call those?
Will it be antibonding?
Not quite antibonding. We call these orbitals non-bonding. But just like filling an antibonding orbital is destabilizing, filling a non-bonding orbital doesn't really provide any additional stabilization. So we're filling these non-bonding orbitals, and that gives us no additional stabilization. So because having these half-filled highest occupied molecular orbitals is so destabilizing, and because we are filling these non-bonding orbitals that don't give us any additional stabilization, when we arrange and we place our pi electrons into these molecular orbitals, we see that overall our electrons are less stable in this anti-aromatic system. And we can conclude that anti-aromatic systems are less stable than conjugated and aromatic systems. Does this idea make sense to everyone?
Professor, can you explain why it's non-bonding instead of antibonding?
Yes. So non-bonding molecular orbitals are orbitals arranged directly at 0 energy. And because our molecular orbitals are arranged symmetrically about 0 energy, in this case, since we make 4 molecular orbitals, 2 of them are arranged at 0 energy, and we call these non-bonding orbitals. So so when you place electrons in a non-bonding orbital, you don't get any additional stabilization. Does that make sense?
And then what's the difference from antibonding?
So antibonding, in this case, antibonding molecular orbitals are higher in energy, and filling an antibonding molecular orbital is dramatically destabilizing. And typically when you start to fill the antibonding molecular orbital, you're essentially describing the weakening of a bonding interaction in your molecule. So filling the antibonding molecular orbital is very actively destabilizing, while placing electrons in a non-bonding molecular orbital doesn't give any additional stabilization. Does that distinction make sense?
Yes, that makes sense.
Perfect. Any questions on anti-aromatic systems from the perspective of MO theory? So 2 things, half-filled homo-orbital, and we typically end up filling non-bonding or anti-bonding orbitals.
I had a question about the octa or cyclooctatrine or tetrine.
Yeah.
So it's not planar, so would we still consider it anti-aromatic?
So despite its best attempts to adopt a distorted geometry, it still exhibits a minor amount of orbital overlap. And even though the molecule itself distorts, in terms of energetics and in terms of heats of hydrogenation, we clearly see anti-aromatic effects at play. So oftentimes for anti-aromatic molecules, they'll adopt distorted geometries or distorted bond length arrangements to minimize this destabilizing anti-aromatic effect, but they can't completely get away from it. So even though it's non-planar, there's still enough orbital interaction for you to see destabilization. So
Okay.
whenever you encounter a problem where you're dealing with a structure, you can treat the structure as if it's drawn in a way where it can be interpreted as planar, you can treat the structure as planar. So in this case, without this additional piece of pictorial information, without this additional information that it actually distorts, we would assume that it's a completely planar molecule. And it would be if it wasn't anti-aromatic. Because it's anti-aromatic, it attempts to distort, to minimize these destabilizing interactions. And despite its best attempts, it still, as we can see, is substantially destabilized by this anti-aromatic arrangement. Does that make sense?
Yes, thank you.
Perfect. Any other questions I can address?
How do we tell when like nodes are being created? Or-
So in general,
Sorry, go ahead.
each time you go up in energy, you generate 1 additional node. So +1 and then +1. So each step up in energy, we see 1 additional node present in our molecular orbital. Does that make sense?
No, not quite. I don't
I,
think.
I guess the better way to think about it is there are many different ways that we can overlap these 4 p orbitals, right? And of the different permutations, some of them will have 0 nodes, some of them will have 1 node, and some of them will have multiple nodes, right? And when we think about how these molecular orbitals are arranged in terms of energy, the lowest energy molecular orbital will have 0 nodes, the next highest will have 1 node, and the highest energy will have the maximum number of possible nodes.
I see.
So rather than think about it in terms of as you go up in energy, the number of nodes increases, think of it as inherently, we're going to have anywhere from 0 to a large number of nodes, and the highest energy molecular orbital will have the most number of nodes. Does that answer your question?
Yes, I think so.
Okay, perfect. So, but in general, as you go up in energy, each time you go up a step, you have 1 more visible node present. Okay, so let's look at our 2 rules for aromatic versus anti-aromatic. A system is considered aromatic if the compound contains a ring comprised of continuously overlapping p orbitals and 4n+2 pi electrons. Aromatic systems are stable since their HOMO orbitals are completely full, their bonding molecular orbitals are completely full, while the antibonding molecular orbitals are empty. Conversely, a ring system is considered anti-aromatic if the compound contains a ring comprised of continuously overlapping p orbitals, and the ring contains 4n pi electrons. So let's apply what we've learned, and let's look at whether the following ring systems are aromatic or anti-aromatic. So we have A, B, and C. So I'd like you to tell me whether they're aromatic, anti-aromatic, or none of the above. So let's take about 3 to 4 minutes to work on this. So what do we think? So we have students commenting, yep, A is non-aromatic. So looking at B, we see a lot of comments in the chat that B is anti-aromatic. And let's talk about why that is. So counting, we have 2, 4, 6, 8, 10, 12. So when we have 12 pi electrons, that corresponds to 4n. When n is equal to 3, that gives us 12 electrons. So it is correct to assign this ring as an anti-aromatic system. For C, we see a lot of consensus in the chat that C is aromatic. Let's talk about why. 2, 4, 6, 8, 10, 12, 14. That corresponds to 4n+2 when n is 3. That gives us 14 electrons. So it would be correct to call this an aromatic system. Do these examples make sense to everyone? Sorry, what do you mean by what compound is C? It in terms of the name, I have to double check to find the formal name for this compound. you commonly see these ring structures as often as part of dyes or molecules that are useful for absorbing light or conducting electricity. So many of these compounds, these large conjugated systems, are useful chromophores. And they actually have some pretty unique properties when it comes to NMR chemical shifts. But I have to get back to you on the exact name of this compound. Any other questions on this example? Okay, so let's keep going now. And let's talk about MO theory and Frost circles. So when p orbitals are combined to yield bonding and antibonding molecular orbitals, the bonding and antibonding orbitals are arranged symmetrically about zero energy. So in order to draw the relative energies of each bonding and antibonding molecular orbital, we use a shortcut. So you draw a circle, you draw your ring inside the circle with one vertex pointing down. You draw a horizontal line representing a molecular orbital at each point the ring and circle intercept. And you draw a dotted horizontal line through the center of the circle. All bonding molecular orbitals are below the line. All antibonding molecular orbitals are above the line. So to show an example for benzene, we have our six-membered ring inside our circle. At each point along the ring where it intercepts the circle, we draw a line. Does this make sense to everyone so far? Okay. So looking at, for example, cyclobutadiene, we see 1, 2, 3, 4 points intercepting. And since we have two orbitals at zero energy, we call these non-bonding molecular orbitals. Now, here's a summary of some common orbital diagrams and their corresponding Frost circle. You are not expected to memorize this. If you know how to draw a basic Frost circle, you can generate all of these orbital diagrams by hand. I'm just providing them here for your reference. So let's look at some examples now where we start to incorporate. What page is that on? This summary of orbital diagrams? It's on page 20 of the notes, but it's not, I don't know if the book has something like this. It could be in the chapter 15 in the book as well. Perfect. So we've primarily looked at systems that have only carbon and hydrogen. Let's start talking about aromatic systems with non-hydrogen atoms, and we call these heterocycles. So we're first going to look at pyridine and pyrrole, and we're going to start and talk about each of these two aromatic systems and their unique quirks. So aromatic compounds can have elements other than carbon in the ring. Heterocyclic compounds contain elements other than carbon in a ring, such as nitrogen, sulfur, oxygen, and phosphorus. The first heterocyclic system that we'll talk about is pyridine and pyrimidine. So as we notice, we have a nitrogen atom in our ring. Now, it's important to consider for a moment, if we take a look at this nitrogen atom, which has a textbook name of a pyridine nitrogen. And if we think about its hybridization, it's an sp2 hybridized nitrogen with a lone pair. And it's really important to consider and to think about, where is this lone pair located? Is this lone pair conjugated, or is it an isolated orbital? So if we have an sp2 nitrogen with a lone pair in general, where is that lone pair going to be located? Is it going to be conjugated, or is it going to be isolated? So we have a pi bond that uses a p orbital. Where is our lone pair located if this nitrogen is sp2 hybridized? It's isolated, yep. This lone pair is not in a p orbital. The lone pair is isolated in an sp2 orbital. And we can see that logically if we consider if this nitrogen is sp2 hybridized, right? We have a total of 3 sp2 orbitals and 1 p orbital, right? In this case, we have used our p orbital already to form our double bond, right? So by definition, the only remaining orbital that we can place our lone pair in is going to be an sp2 orbital. And for those who can say, can't we adopt an sp hybridization? 180 degrees is not compatible with a 6-membered ring. Does that explanation make sense to everyone? Does everyone see why this pyridine lone pair is isolated? By the same token, if we look at pyrimidine, again, we have 2 nitrogens in our ring. In each case, the lone pair is found in an sp2 orbital. If we think about pyridine and pyrimidine, the pi electron structure resembles benzene with 6 electrons, and the nitrogen lone pair electrons are not part of the aromatic system. One thing that I just want you to note, it doesn't come up in this class, but it's important to consider, is that heterocycles exhibit weaker aromatic stabilization. They're still quite stable, but it's not as strong as your typical carbon-based aromatic system. And it has to do with the fact that nitrogen's orbital energies are a little bit different than that of carbon. Any questions on pyridine and pyrimidine? Now you may say, why does this matter? Well, pyridine is a relatively weak base compared to normal amines, but protonation does not affect aromaticity. So for example, if you take pyridine and you treat it with, for example, hydrochloric acid, which has a pK around -3 to -5, you will end up generating the pyridinium hydrochloride salt. Now, thankfully, when we think about this pyridinium salt, our starting material is aromatic. Is this pyridinium salt also aromatic? Is this compound still aromatic? Yes or no?
Yes.
Yes, yep. So then, even though this pyridinium salt is still quite acidic, as a pK around 2 to 3, it's quite an acidic species, we still have an aromatic system. So protonation doesn't dramatically affect aromaticity in this case. Now, why am I bringing this up? Well, we're going to look at a follow-up example of pyrrole and imidazole, where our lone pair has dramatically different properties. So looking at pyrrole and imidazole, these are 5-membered heterocycles with a nitrogen atom. Pyrrole has 4 sp2 hybridized carbon and has 4 pi electrons. The nitrogen atom is sp2 hybridized, and the lone pair of electrons occupies a p orbital for a total of 6 pi electrons. So this is an aromatic system. Now, the pyrrole nitrogen is sp2 hybridized, and compared to pyridine, for our pyrrole nitrogen, our lone pair, instead of occupying an sp2 orbital, is placed in a p orbital, because we've used our sp2 orbitals for bonding. So this lone pair is delocalized throughout our aromatic ring. Does everyone see that? Now, if we look at imidazole, imidazole is quite interesting because it has a characteristic pyrrole nitrogen and it has a pyridine nitrogen. So this nitrogen in the upper right corner is a pyridine nitrogen. And the reason for that is if we look at this upper right-hand corner nitrogen, what orbital is this lone pair found in? What orbital is that lone pair found in?
SP2.
sp2, right? So it's an isolated lone pair. Comparatively, if we look at this bottom nitrogen, that's a pyrrole nitrogen, and it's located in a p orbital. So it's a delocalized lone pair. So if we think about basicity, and if we think about which of these lone pairs is going to be the most basic, which of these lone pairs are the most basic? And we already have students typing that they suspect this top lone pair, considering it's isolated and it's localized, would be the most basic lone pair. And that would be correct. Yep. Does that idea make sense? When they talked about acid-base chemistry in your previous class, did you ever hear the term pyridine and pyrrole nitrogen brought up?
No.
No.
Okay. So essentially a pyridine nitrogen is a localized lone pair, while a pyrrole nitrogen is a more delocalized lone pair. In general, pyridine nitrogens are more basic. Now, there's another reason why pyrrole is such a terrible base, or it's worse than you would expect. So if we think about pyrrole versus like a conjugated amine, pyrrole is way less basic. And the reason for that is that protonation disrupts aromaticity. So if we treat pyrrole, for example, with hydrochloric acid, we start off with an aromatic ring and it's quite stable, right? If we treat it with hydrochloric acid and we generate the hydrochloride salt, is this system still aromatic?
No.
No, it's non-aromatic. And in turn, if we think about this equilibrium will massively want to favor our reactants over our products. We're fighting an uphill battle here. And as a result, this protonated pyrrole is very acidic. A pK of about -3 to pK of around -3. It's very hard to protonate pyrrole. And it's much more difficult than you would expect. So the main distinction between pyridine and pyrrole is that protonation of pyrrole breaks aromaticity. And as a result, it's much more difficult to protonate pyrrole. Does that make sense?
Yes.
Perfect. So this is a good stopping point for today's lecture session. So I'm going to pause the recording. And what we're going to do is we're going to take a quick 10-minute break and then resume in the same call for laboratory.